Okay, hi class. So let me say a little bit about where we were last time. Okay, so last time at the end, we had defined intervals in R. Okay, so this was just given A, B, and R. We could form, well, the closed interval AB, the open interval AB. I guess I'll write down the possibilities. And these were all depending on some order relation between A and B, right? So this were X and R that are between A and B. This was the X and R that were kind of strictly between A and B. And then these were other possibilities are defined analogously. Okay? And then we got to the idea of nested intervals. Which were just intervals contained in one another. And we thought of these as a method to zoom into points on R. Okay, so let me do an example, which is I could look at the nested intervals 0 to 1 over n for n and n. Okay, so usually when you're looking at a nested intervals, you're looking at a sequence of nested intervals, so they're naturally indexed by the natural numbers. And we can think of 0, 1 over n as zooming into 0. In particular, the intersection of all of these is 0. Okay, so if you imagine that you're an element of the real line and you're constrained by having to live inside these intervals, then what you're forced to do is get closer and closer to 0 as you go. Okay, so if I'm forced to live inside these intervals, I have to be getting closer to 0, and in the limit, I just get, or in the intersection, I get exactly 0. Okay, so let me just note that there are other possibilities, which I will kind of leave as exercises to say exactly what can happen. So for one thing, we could look at the interval, say -1 minus 1 over n. Oops, sorry. That was written pretty terribly. -1 minus 1 over n. 1 plus 1 over n. Okay, this could be my nested intervals, and then, it's a natural question, what do you get for the intersection in this case? Okay. You also don't have to do closed intervals. Okay, you can do this with open intervals. But let me just note that sometimes when you do this for open intervals, you don't get anything in the limit. When you do this for open, the intersection is empty. Okay, so for example, you could look at just the open interval from 0 to 1 over n. Okay, so now all of these are non-empty, and if I take a finite intersection of them, I'll get a non-empty set. Oops. So now I'm looking at intervals that look like this. So I'm kind of happy and I see something non-trivial in every intersection until I take the intersection of all these sets, and then I just get nothing. Okay, so if you want to prove this, it basically follows from what we saw before for any x in the real numbers, or in 0, 1 in particular. So I should say in the positive reals. There exists a 1 over n, so that 0 is less than 1 over n, less than x. Okay? And then x can't be in that interval. So for any x you choose, you're eventually going to get a smaller 1 over n, so x won't be in the intersection. Okay? So the kind of remarkable thing, remarkable fact, I think, is that if you take these nested intervals to be closed, then you always get something in the intersection. If you take a sequence of closed nested intervals, so I hope I probably did this without thinking about it. So closed always means where I include the endpoints. Okay, open is where I don't. If you take a sequence like this, which is nested and has infinite intersection, then the intersection is not the empty set. Okay? So if I do this for closed intervals, what this theorem is saying, or this fact is saying, and we'll prove it soon, is that you always see something in the intersection, no matter how you nest them. This turns out to be, as I said, something that's not true for open intervals, and also isn't true, so this is not true for the rationals. Okay, and we'll see that soon. Okay, so this is called the nested interval property of R. And so we're going to prove this. As you can guess, since it happens to not be true for the rationals, this proof is necessarily going to involve completeness. Okay, so maybe I'm going to pause here. I want people to think about what are some ideas for how you could find this element, inside the intersection of these nested intervals. Okay, so I'll pause here. Okay, so let me prove this now. It turns out it follows pretty quickly from completeness. Okay, so first note, so let me just give some notation. I'm going to write I sub n to be A sub n, B sub n. Okay? And what we know is that I have these sequences, A1 less than or equal to A2 less than or equal to A3, and so on. And B1 is greater than or equal to B2, greater than or equal to B3, and so on. So this is by nesting. Okay? So I'm just saying take the right endpoints. I'll add them to the picture here. Oh, I guess those are the left endpoints. Take the left endpoints, take the right endpoints. You're going to have an increasing sequence of numbers on one side and a decreasing sequence of numbers on the other side. Okay? So note that the set of AN, so these numbers of these left endpoints, is bounded. Why is this? Well, the intervals are nested. So AN is contained in I1. So IN, is contained in I1. So in particular, AN has to be less than or equal to B1 for all n in n. Okay? It's also not empty. So therefore, by completeness, it has a sup. Okay? So therefore, the set of left endpoints has a sup. which I will call x. Okay? So you can think of the soup as a natural candidate for something that's in the intersection, right? This is I1, or A1, A2, A3. If I want something in the intersection, it seems like the left endpoints are converging in some sense to that element in the intersection. So what it should be is just the soup of those elements. Okay? And what we want to show now, so the claim is that this works. Okay? So we need to show that it's in the intersection, which means that we have to show that it's in the nth interval for all n in n. Okay? So how do we do this? Well, we have to show two things. To show it's in In, we need that an is less than or equal to x, and x is less than or equal to b sub n. Okay, so the first one is pretty clear. So maybe I'll say this. We chose x to be the soup, so since x is the soup of the set of the a sub n's, it obviously is bigger than all the a sub n's since it's an upper bound. Okay? So kind of the work is to show that x is less than or equal to bn. Okay? For all n. And how do you know? So you have something which is a supremum. You want to show it's less than something. The way that you show a supremum is less than something, so to show x is less than bn, you have to show that bn is an upper bound for the set an. Okay? So that's just, if you want to show something, a supremum is less than something, well, you should show that that something is an upper bound for the set that you're interested in. Okay? So how do we do this? Oops, let me try to move this. Okay, so we want to show that for any, maybe I'll switch it to k. So for any k, bk is an upper bound of the set a sub n's. Okay, so notice that there's kind of two different values here. So you can take an where n is less than or equal to k, and an where n is greater than k. Okay, so maybe I'll just redraw the picture here. If I have this sequence of nested intervals, I'm looking at a specific one, bn. Well, there's two kind of different cases, right? There's either the an's which lie before it, and then the an's that lie after it in the sequence. Okay, so what about the first one? So you want to say something like this one, where it's less. Oh, sorry, I switched my k's and my n's. So this is bk an. So the first one, if n is less than or equal to k, then what we have is that this interval contains the kth interval. And then what we know, so we know a sub n has to be less than or equal to a sub k, right? Because an is here, ak is here, and that's less than or equal to bk. Okay, so it's an upper bound in that case. For the other case, you have that n is greater than k, so you're somewhere here, an is kind of a further left endpoint of something that's further nested in the sequence, then what you know is that, well, so I, k contains in. If I'm looking at a sub n, it must be less than or equal to b sub n. But since I sub k contains I sub n, this is less than or equal to b sub k. Okay? So therefore, we have shown that b sub k is an upper bound. And this works for all k. Okay? And therefore, so what you can imagine is if I fix an endpoint here, I'll just, redraw the picture. Again, we have the b sub i's, or b sub k's, as a decreasing sequence. Of course, it doesn't have to be strictly decreasing. I know that like b1 could equal b2, for example. But every one of these b sub i's is an upper bound for every single a sub n, right? So the a sub n's are never going to get greater than one of these intervals because that would contradict nesting, okay? And therefore the sup of the a sub n's is always bounded by any of these, so you have to have that's in the intersection of all, okay? So therefore the supremum of the set is in the intersection. And notice that this proof basically would work for the rationals, except for the fact that the sup might not be a rational. And then, so you might have like where the sup is square root of 2, and then you have to leave the rationals and go to the real numbers. Okay? So that's the proof, though. Okay, so as you may have guessed, we are going to get to sequences soon. Okay, just because, well, they naturally come up when you're looking at nested intervals, and we'll see that they have naturally are going to be useful for what we want to do later. So I'm just going to give a lecture problem here as kind of a warm-up for sequences, and it's an interesting sequence. Okay, so let me define a sequence of real numbers for you. So I'm going to say f0 is 0, f1 is 1, f2 is 0 plus 1, so it's 1, f3 is 1 plus 1 is 2, and f sub n is equal to f sub n minus 1 plus f sub n minus 2. This is called the Fibonacci sequence. And what I want you to prove, so for all n and n, we have that the sum of the Fibonacci numbers, so if I look at the sum from 0 to n of the s sub i's, is equal to f sub n plus 2 minus 1. Okay, so if I look at f0 plus f1 plus all the way up to f sub n, I'm getting f sub n plus 2 minus 1. Okay? Okay, so now let me just, I want to prove kind of one more thing, though, before we start defining sequences and working with them. So let me just prove first a refinement of the above property, or the nested interval property, which I'm going to call NIP. Okay. So as I said, you can kind of, these nested intervals can be a variety of sets, right? So it turns out if I look at minus 1 over n, 1 plus 1 over n, this intersection is just the interval -1 to 1. Okay? So it's going to be useful to have a criterion for when the intersection of sets isn't something larger than a single point, but is just a single element of the real line. Okay? And the way that you do that is that, well, you ensure that the intervals have to be getting shorter and shorter, right? So notice the intervals here are getting long, are staying reasonably long. The criterion is if you have that the intervals are getting shorter, that they have to intersect in just a single element, okay, which will be useful. So here's the theorem. I'm going to leave it, it's going to be on the next homework assignment, okay? So if I sub n is an, Bn is a nested sequence of closed intervals. And what I want to say is that the lengths limit to 0. We haven't talked about limits yet, but it suffices to show that such that the lengths, or the way I can write it is the lengths Bn minus An satisfy the infimum of the set of lengths is 0. Okay, so notice the lengths are all, these are all positive numbers. They're actually decreasing since you have a nested sequence of intervals. And what we're saying is that the infimum is 0. Though it doesn't have to, honestly be 0, right? It could just kind of approach it. Then the real number x in the intersection is unique. Okay, so in other words, the intersection is a single point. Okay, so I'm gonna, as I said, that's gonna be on the homework. What I want to now bring it back to, though, is that these ideas of nested intervals are related to something that we've seen a couple weeks ago. So are related to countability or uncountability of the real numbers. They imply that R is uncountable. Okay, and notice this is somehow, so I'm going to prove this. We're going to give a new proof of the uncountability of the real numbers. So new proof that R is uncountable. But notice this is somehow going to be a better proof, because when I did it before, I had to say, well, R is, this set of decimal expansions. We didn't have a exact definition. Here, what I've told you is R is the set. It satisfies these axioms. It has this ordering, and it's complete. Therefore, it's uncountable. So therefore, what we're using is somehow the axioms plus ordering. It's like the plus multiplication axioms plus ordering plus completeness implies uncountable. Okay, so the book might say, well, every complete ordered field is uncountable. Okay, but I would just say, well, this is, you need these three things, and you cannot have these three things on a countable set, which is kind of remarkable. And okay, so to prove this, we're going to, again, I'm just going to show that 0, 1 is uncountable. So we're going to do proof by contradiction. So suppose that 0, 1 is countable. So I can write down this list of elements. Okay, so if it was in bijection with the natural numbers, I would be able to say what gets sent to 1, what gets sent to 2, and these are my elements here that I can list down. Okay? So let me draw the picture here. So I'm going to put 0 and 1 here. And then I take my element x1, which, maybe is sit here. I have no idea where it is, but it's somewhere between 0 and 1. Then what I'm going to do is just take any interval, I1, so take I1, so that x1 is not in I sub 1. Okay? And now rinse and repeat. Okay? So maybe I should say, how do you know that you can find this I sub 1? This just follows from this density theorem. So I had to use, if you want, I had to use the fact that the rational numbers are dense. So you give me an element here, I can find an interval which misses it. I can even assume it has rational endpoints if I want. Okay, so now for x sub 2, we take the interval I sub 2. Well, let's be a little bit more careful. So first, x sub 2 should not be in I sub 2, and I sub 2 should be contained in I sub 1. Okay, so you want a nested interval which misses x sub 2. And there's kind of two things you have to worry about, right? So first, x sub 2, we really don't know where it is. It could be right here. It could be missing I sub 1 itself. It doesn't matter. You just take I sub 2 contained in it. Now, what could happen here is that, if you want, you could just take I sub 2 to be I sub 1 in this case. Or what could happen, is that x sub 2 is in here. Right. Well, again, just do the same thing. Find a smaller interval here, I sub 2, so that x sub 2 is not in there. And now we do the exact same argument. So rinse and repeat to get a sequence of nested intervals, I1 contained in I2, contained in I3. If I want, this isn't necessary, but I can also assume that the lengths have infimum 0. Right? I might not have to do that by this procedure, but I can certainly choose intervals that are getting shorter and shorter. Okay? So now, this nested interval property implies that there exists some z in the intersection of these intervals. Okay? And the claim is that z is not equal to xn for all n. And of course this has to be, right, because z is in every single interval and x sub n is not, right? So this is because z is in in for all n and xn is not in I sub n. Okay, so they can't be the same element. You can think of this as kind of like some sort of diagonalization argument, right? You're finding something, this element z, which on one of the intervals has to differ from any element of your sequence. And if they're not in the same interval, then they're not going to be the same element. Okay, so that's the proof. Okay, so now I want to at least say a little bit about sequences now, and then we'll be done with the video. So we can think of this as another way to zoom real numbers, right? So instead of intervals now, we're going to start zooming pointwise. So we start zooming into points just by using other points. So here's the picture. You have some sequence, which just is going to be, well, I'll define it precisely in a second. We're taking a bunch of real numbers. We think of them as approximating a real number that we're interested in. And there you can kind of get properties of the real number based on properties of the sequence. Okay? So what's the definition of a sequence? So it's just a sequence of real numbers we can define it kind of simply, or without too many words, is just a function from the natural numbers to the real numbers. Of course, I usually think of the sequence not as a function, but you can sometimes identify with the image. All right, so the image is just this, a natural's worth of points in the real numbers, okay, which we kind of think of the sequence as rather than as this function. Identify with the image. Okay, and then the value, so f of n, is going to be usually denoted by x sub n. Okay, so these are the terms of the sequence. And the other way that you can denote this, the entire sequence, is as, I mean, we're kind of using open parentheses too much, but that's just common notation, or maybe x sub n, where n is in m. Okay, so notice this is different. This is different from the set x sub n. Okay, so in particular, this set doesn't have an ordering, right? It just is, it's a set of real numbers. In this one, this is a function from the naturals to r, so you can think of it as an ordered sequence of numbers. Okay, so this is, maybe I'll just write this. Order matters here, and it doesn't matter here. Okay? Okay, so just to, be overly pedantic about it, let me just write down the example. If I look at the sequence -1 to the n for n and n, this is not equal to the set -1 to the n for n to the n. In particular, this is 2 points, right? This is -1 and 1, and this is a sequence. Let's see, -1, 1, -1, 1, and so on. Okay, so you can think of this also, if you want, as some element of in some infinite Cartesian product, but I'm just going to think of it as a function from n to r. Okay, so what we're going to need now, we want to talk about convergence. of a sequence. And for that we need a notion of a distance in R. So we need distance in R. Of course we have essentially defined this as lengths of intervals. But that, again, we only did that for A being, less than B. In general, you just use the absolute value. So we need a distance. So let me just recall for people, the absolute value goes from R to the positive reals. And it's just defined to be A if A is positive, 0 if A is 0, and negative A if A is less than 0. Okay, so in particular, it's always a positive set. And then the distance between A and B is defined to be the absolute value of A minus B. Okay, which is the same as the absolute value of B minus A. Okay, so let me just give you some basic properties of this absolute value. Okay, so the first is that it's always greater than 0. Okay, that's straight from definition. The second is that I would check some of these. I'm going to leave one of them as a lecture problem. Okay. So the absolute value of AB is the absolute value of A times the absolute value of B. The absolute value of A squared is just A squared. If I take any positive number, then what I know is that if the absolute value of A is less than or equal to C, I get that A is between minus C and C. So in particular, I have that minus the absolute value is an upper bound or lower bound of A, and that's an upper bound, and there's an upper bound by the positive absolute value for all A and R. I guess this was also for all A and C and for all A and B. So finally, let me just give you kind of the key property, which I'm going to leave. It's a useful exercise to prove, so I'm going to leave it as a lecture problem, which is the triangle inequality, which says, in this context, for every A and B in the real numbers, if I take the absolute value of A plus B, it's less than or equal to the absolute value of A plus the absolute value of B. Okay, so that I'll post this as a lecture problem. Okay, so I think the natural thing now is to go into convergence, but I think I'm going to stop here and do that on the next lecture. So, thanks.